From the TAPR DCC in Albuquerque 2018, a flexible, affordable, and powerful digital transceiver for the Raspberry Pi, starting now. Hi everyone, good evening. My name's Jason, I'm KC5HWB. This is Ham Radio 2.0. If this is your first time here to join us, please click on the subscribe button below so that you can keep up with all the videos that we do. This is the 5th episode I've put up from the TAPR Digital Communications Conference in Albuquerque 2018, and this is given by Jonathan, KF5IDY, about a powerful, affordable, and flexible digital transceiver for the Raspberry Pi. There was quite a bit of Raspberry Pi stuff at the TAPR conference, and I enjoyed every bit of it. So check out this video and leave your comments below. 73.
All right, so Jonathan Bradenburg, KF5IDY, his talk is a flexible, affordable, powerful digital transceiver for the Raspberry Pi.
Could we possibly have sold it any better than that? Flexible, affordable, powerful, digital, helps you lose weight, grow back your hair. At that point, I know it's a little bit beyond real. I would too. I would definitely take it. So, Jonathan Bradenburg, by day, I am a senior lecturer at the University of Texas at Dallas in their computer science department. By night, I like to build and launch satellites, specifically digital communication satellites, which explains my talk today. So let's begin by understanding why I'm interested in this particular topic. And if I asked you what do the following have in common, we could start with AMSAT, specifically AMSAT NA, the North American AMSAT organization. I could add to that the Libre Space Foundation. Who's heard of the Libre Space Foundation? It's a foundation that focuses on open source space technologies. SatNogs, for example, is one of them, an open source rotator and a around the world network to receive automated communication. And then let's throw in a couple of other organizations, the University of Louisiana, maybe you've heard of them, some of us, and then the Portland State University. So what do they all have in common? Well, they all have in common that they're using this same digital communications chip for their technologies, the AX5043 digital transceiver IC. AMSAT, for example, is using it as the digital transceiver for their flight CPU, the IHU, for their next Golf series of satellites. They're flying 2 of these digital transceiver chips on that satellite in a failover configuration. Libre Space Foundation is building a series of PCBs and boards no bigger than this remote control here that contain a CPU and a digital transceiver chip for flight on balloons and in spacecraft. University of Louisiana is using it for a satellite beacon for a satellite they're hoping to launch. And then Portland State University is using it in their AuraSat project, their primary communication platform for their satellite. So it's getting a lot of press. I'm focused mostly on the space aspects of it, but there's certainly a lot of other opportunities to use this chip. So I've kind of introduced it. It's a small chip, about a 1/4 inch on the side, being used by all these. So what is it? Now I've said who's using it. Why are they using it? Well, it's a single chip, low power digital transceiver. Okay, so what does that mean? It means that it is an entire radio on a chip. It's doing all of the hard radio functions. The modulation and demodulation is performed on the chip. So I don't have to worry about modulating at FM, modulating at PSK, modulating at AFSK. I just tell the chip to do it and magic happens. And what that means is when I'm using this chip in my projects, I just pump in data. I pump in my name, I pump in my lat long, I pump in data, and this chip takes that data, adds forward error correction, adds preambles and error correction, and then transmits it out in a modulated fashion. So I don't have to deal with any of the radio aspects of it. I get to use it as a digital radio. And then on the receiving side, the AX5043 receives the signal, demodulates it, checks it for errors, corrects them if it can, and then checks the CRC. And if the data is good, it sends it to me, and I use it. So it's a chip that goes on top of a single board computer, much like you saw this morning with Scotty's. One of the questions you might have is, okay, great, it modulates and demodulates, it sends data magically through the ether. What modulations does it do? And that's of interest to all of us, I'm sure. And here's a list, right? It's a fairly long list. I just tell the chip, modulate FM, and it does it. I tell the chip to modulate PSK, and it does it. I tell it to modulate FSK, and it does it. It supports a lot of different modulations all by itself. So what are some of the capabilities of this chip? Well, it's a very broad frequency range. It goes anywhere from 27 megahertz to over 1,000 megahertz, so quite a broad range. It covers a lot of the ham frequencies, if that's what we're interested in. Specifically, it definitely covers the 2 meter and the 440 quite nicely. What about power? How much can it output? The chip itself outputs 40 milliwatts, 16 dBm. I think I got that math right. Somebody out there will correct me if I got it wrong. 16 dBm, about 40 milliwatts. It has built into it a small amplifier in this chip that will output that just bare. But of course you can add an external power amplifier, which is exactly what I think we should do. What about sensitivity? I mean, if it transmits, can it receive? These numbers, negative 138 dBm, if it's transmitting data at 100 bits per second, seems pretty good to me. Negative 108 dBm if you're transmitting a lot faster, like 125 kilobits per second. So it's a very sensitive receiver. In fact, in my little home office, that's caused me a challenge now and again because I'm trying to isolate this from other equipment. And so I'll put it in a steel box and I'll put solder on the side and I'll try to put a connector on the outside. And darn if it still doesn't somehow escape my homemade Faraday cage. But the sensitivity is so great that it picks up just about everything in the room. And then one of the things I said early on is that this is a low power device. It doesn't require much power, making it very appropriate for mobile devices, IoT devices, satellites, that sort of thing. And so we can talk a little bit about its power requirements in the milliamps when it's active. So to receive, it needs somewhere in the range of about 8 milliamps of power, so fairly low power. Transmitting, it doesn't require much more than 8, just really what you're transmitting. So at most, you can see that we've got about 48 milliamps when we're transmitting the 40 milliwatts. Seems reasonable. But what makes it super special is it has some low power modes. So if I want to put a radio in a device, and I want that device to have a long battery life, I can put this chip to sleep. And in its low power mode, we're talking nanoamps. 50 nanoamps is what its lowest power mode is. And it wakes up, receives or transmits, goes back to sleep. Wakes up, transmits, receives, goes back to sleep. So this is a very, very cool chip. It's being used in a lot of cool projects and things that I want to play with. So if you wanted to get involved, what would you do? You'd probably build a board that had this chip on it. Of course, you're a lot more experienced at such things than I am, but that's exactly what I did. So I did develop, as an experimental platform, a board for the Raspberry Pi that has there in the middle, you see the little black square? That's my little AX5043 chip. So I wanted to build a board that I could experiment with and expand upon for use with this digital transceiver. And I decided to put it on the Raspberry Pi. Why did I put it on the Raspberry Pi? Well, Scotty talked about it, so it's got to be good. He put Raspberry Pi on his list. And he put it on the list for the same reason I use it a lot, is because it's a very common, affordable platform. The bare bone Raspberry Pi computer is $30, $35. If you have a keyboard and mouse laying around, there's no additional cost there. But it's a very, very affordable platform. It also has the peripherals that I need to communicate with this AX5043. This AX5043 chip uses the SPI bus, SPI bus, to accept commands and data from the computer it's hooked up to. So what happens here is my idea is that I would write some software that runs on this Raspberry Pi. That Raspberry Pi transmits data and commands through the SPI bus to that chip, goes out into the ether. Another one of these receives it back. The Raspberry Pi gets the signal and is able to decode it. So that's the route I chose on this one. And I like the Raspberry Pi because it has extraordinary community support. There's a lot of them out there. A lot of people use them. It's going to be around for a long time. Now, that all sounds easy. I would build a board, I say. Except I've never built a board before. So I've never drawn a schematic before. I know, hard to believe. I said I worked as a senior lecturer at the University of Texas in Dallas. I work in the computer science department, which means I write software, and we're afraid of things like resistors and capacitors and solder. We don't touch those things. Except I wanted to overcome that phobia. Is there a phobia name for that? There probably is. I wanted to overcome that phobia. What is it? Resistophobia? That works very well. Resistophobia. So I wanted to learn how to do this, and this seemed like a perfect opportunity. So I jumped right in, and I drew a schematic. And this schematic is not that frightening to you, but I cannot tell you how proud I am. I probably strutted around the house for a week when I finished this schematic. My wife was annoyed. There you go in all of its fine glory. And I ended up using and learning KICAD. KICAD's becoming a fairly popular schematic and layout program. I see some thumbs up out there. Eagle was the open source favorite for a long, long time until some people grew annoyed with its acquisition by a commercial entity and its subscription program. I used Eagle for a little bit. I liked KICAD. I went ahead and stayed with KICAD. So I learned how to use KICAD. Draw up a little picture here. And really the entire schematic consists of the AX5043 chip right there in the middle, along with a few thingy boppers coming out of it. That's my technical term for them. Matching network. The Raspberry Pi connector off there by itself just to make it readable. Oddly enough, that little piece right there, if you can see it on the screen, that's a power LED. I learned how important it is to know when your device is on. Ended up putting a power LED on there. And then borrowing from a friend of mine, just because I thought it was useful to have something to transmit, I ended up putting a small temperature sensor on this board as well. So this board has a temperature sensor to give me some data, a transmitter to transmit that data, and an LED light to know when it's all turned on. So ended up drawing that in KICAD and was quite happy with it. But once you draw it in a schematic, then you have to lay it out. And if I thought learning to draw a schematic was hard, learning to lay something out is a lot more difficult. But I was successful, and OSHPARK did me the generous favor of drawing these renders for me. So there you go. I even did things like, ground stitching, sort of. See the little holes there? Turns out to be fairly hard in the version of KICAD I was doing, but I got that to work. Ended up being a 4-layer board, maybe a little excessive for something like this, but that allowed me to put a ground plane and a data layer and a power layer separate from the signal layer mostly. So that gave me a lot of opportunity to kind of separate those different signals. So then you send off for OSHPARK, they send you a lot of boards for cheap, and then you get to assemble them. So I actually talked to a local assembly house in Dallas about putting these boards together for me. And they said they would do it for the price of about $200 a board. I know. Well, I was looking at small quantities. Now, if I wanted to go up to 25 boards, they'd only charge me $50 a board to assemble them. That's still a bit of money out of my pocket, so I decided to assemble the boards myself by hand. Now, these are 0603 components, so they are hand solderable if you really wanted to get down to it. I've done that with some kits. But the AX5043, those little footprints right there, those are a little too tight for me, although I know people that can do it, especially when you got the ground pads underneath it. So I decided to go a different route. Let's learn how to reflow. So I went on to Amazon, the source of all magic, and ended up buying both a microscope, and they called that an IC heater, but I call it a reflow oven. Ended up hand assembling under that microscope, which is a fantastic tool to have in your toolbox, and then popping it in that reflow oven. To date, I've assembled about 15, 16 of those boards, and every single one of them has been successful. It takes me about 30 minutes per board to get the components put out on there and through the oven, and I have great success. Now, it's not like I'm going to give them away for Christmas presents or anything. It's a little too much work for that, but it's enough that it's something we can play with. Of course, the proof is in the pudding. After I've done all this work of schematicking and laying outing and board manufacturing and assembly, does it work? And of course, I wouldn't be here, probably, unless the answer was yes, of course it works. That's good news. Was there ever any doubt? Maybe. So I developed some sample applications on the Raspberry Pi. Being a software guy, that was not too scary for me. Raspberry Pi runs a Raspbian operating system, the Debian Linux distribution, has some fairly good libraries for communicating with the GPIO pins in the SPI bus. And I ended up early on developing a chat application. So on one of these Raspberry Pis, I'd have a keyboard, and I would type a message, and across the room, another one of these boards would receive it and display it on the screen. And sure enough, it worked. First one I used for no good reason was I coded it with GFSK. GFSK? Yeah. I think that's right. About 435 megahertz with 4,800 symbols per second. We might call it 4,800 baud. HDLC encoding with CRC16. And I thought that was pretty fancy because I could chat across the room on a board that I built. And it works really, really well. But I also got to thinking that if it's HDLC, that sounds an awful lot like APRS or other types of AX5045, 25 encoding, AX25 encoding. So I ended up writing a version of this software that actually was successful in transmitting fully configured APRS frames using AFSK with the X.25 format. Now the frequency I was using was still 435.3. And upon my research, and you all know this better than I do, I'm sure, that when you're talking about 440 megahertz, typically APRS is transmitted as FSK, not AFSK. Does that sound right? Typical habit? Yeah, 9600, FSK, that sort of thing. But it turns out I really, really, really wanted to do audio frequency shift keying, AFSK, so I went ahead and coded this as AFSK. The reason I ended up using AFSK was because I wanted to. The reason I used 435.3 had to do with the way I built the boards, which we'll come back to that here in a second. So after all this journey, because we told about journeys, talk about your journey, learning how to do schematics, learning how to do layouts, working with this really cool and powerful digital transceiver chip, what did I learn? Well, I learned that documentation is important, is one of the things that I learned. Because it turns out that the documentation for this AX5043 chip is not exactly complete. It's what I would call, I think I talked about it up here, as a reference, not a guide. Who remembers a good old AT&T System 5 Unix? There's a few hands that go up. Didn't they used to come in those red softbound books with the spiral binding that you could read? They had guides and manuals, right? This goes to show how popular I was when I got out of college because I would sit at home and read those on the weekends. And I learned the difference between a reference and a guide, because what the reference would be a list of commands and a list of options for those commands. And then what the guide was how you put those together and how they work and how to use them properly. It turns out that the documentation for the AX5043 is definitely a reference. It tells you what all of the registers do, it tells you what all the commands do, but it doesn't actually tell you how they go together, how they fit together, or how to use them. And that turned out to be a genuine challenge. Because if they don't tell you how to use them, how do you figure it out? What was the answer? Guess? Trial and error? Trial and error is absolutely one way to do it, but they also, onsemi, the maker of the AX5043 chip, has an application they call AX Radio Lab. And with AX Radio Lab, you've got this really cool Windows application, if you love Windows applications, and you say, I want to develop a radio, and I want it to use FSK, and I want it to be at this 9600 baud, and I want it to be at this frequency, and I want it to be with this modulation index. And you push a button, and it spits out the software that does that. And that sounds pretty cool, except their software is specific to a very single processor, the on-semiconductor AX8052F100. And if you're not using that processor, you indeed do end up reverse engineering their code to understand what they're doing and how they're doing it. It also had the distinct disadvantage that this generated software they used also depended upon interrupts. And on some of the single board computers we're using, like the Raspberry Pi, it's possible to use interrupts, but it's not exactly easy. So you'd almost prefer to use some sort of polling mechanism. So I did go through the incredible pleasure and fun of rewriting their code to avoid interrupts and to work on pretty much any processor, regardless of the processor architecture. So that was part of the learning experience and a lot of the opportunity. I did kind of lie to you just a moment ago, because I said, I know, stone me now. But I noted that their documentation was a reference, and I said it described what all of the registers do and what all of the commands do. Well, it turns out it doesn't. At the bottom of the reference guide, it actually says there are these registers like F00 through F3F. Yeah, we're not going to tell you what they do, but just do whatever the software spits out. So there's several registers that you only set based upon what their sample application generates. It's almost as if they couldn't figure out how to document those, so they just said, yeah, whatever comes out, use it. So there are a couple of challenges with the AX5043, but that's, that's part of the pleasure. It is an incredibly powerful chip, it's incredibly popular, and once you learn how to use it, once you figured out that first pass, it actually is very easy. You just have to get past that initial hump. I'm going to pause for just a fraction of a second if I can. Is there a mic nearby? Because I like to take questions in the middle as long as I have time, and I do. Right over here.
Let me get to you there, Tom.
Is the chip half duplex?
Yes, thank you. I do mean to mention that, Tom, and I think you know the answer to that. It is half duplex. That's absolutely right.
And so how do you TR switch with your remote external amplifier?
Okay, so the great question is on the, if it is half duplex, which it is, how do we transmit receive switch with an external amplifier? Now, I'm not using an external amplifier on this chip, on this particular board. So all I do is I just simply switch the chip back and forth between transmit and receive. And it works really, really fast. It's got a switching speed of like a millisecond or a half a millisecond, something like that. If I did have an external amplifier on it, it actually has two different antenna ports. One is receive only, correction. One is transmit only, and the other can be used for either receive or transmit. So what I end up doing is using one antenna for receive and the other for transmit. That's how I solve that problem. Yeah?
How come you chose this particular chip? Like, I've done some work directly and indirectly with different FSK and FSK-like modems on a chip, and I tend to see a lot of Silicon Labs, Semtech, and TI ChipCon products. What's the advantage of this part?
Yeah, I have, you're asking how I chose this chip, and I would like to tell you it's because I did an exhaustive survey of the field and chose this chip because it met all the requirements. And the answer really is much simpler than that. It's because a colleague of mine started building a satellite around this chip, and so I decided to learn it. But having said that, I can kind of justify myself and justify its use by the fact that it is an incredibly affordable chip with a lot of power to it and a lot of range. So we're talking, in quantity, you can get this for $3.50, something like that. So it's a good cost benefit.
Another question, have you considered, so you did one for 70 centimeters, right? Have you considered doing one for perhaps 2 meters, or I was even looking at the data sheet, it actually goes down to like 6 meters.
So have I considered other bands? And I'm going to ask you to hold off on that question until I take one more first, and then I'm going to continue the presentation. Okay. So hold off on that one, and let's hear this one.
I saw the lower end of the frequency was CB, basically. I wondered if you'd check that out and seen if you can go any lower. I mean, could you do 15 meters, for instance?
Oh, a great question. So you saw that it's what, 27 megahertz was the low end of this. Is that a hard limit, or does it go lower? And I have to completely admit I have not investigated that, so I just simply don't know the answer to that. So we started to get into some questions. I'm going to go ahead and continue the presentation, but I'll come back. I'm going to go ahead and, since you asked the question about frequency bands, I'm going to go ahead and talk about that a little bit. I did develop this board based upon about 433, 435 megahertz. And the reason, again, I did that is because our initial designs for the satellite had us using that band. But I was interested in much broader ham frequency discussions. And so a lot of this board and a lot of this chip is based upon the matching network that we have coming out of the chip. And this is going to be a little hard to see, but I'll explain it. So here on the left, we have a differential antenna output coming out of the chip and into the chip. That's the receive transmit antenna, so it goes out and in. And then there's this matching network and a whole table of components here. And now you really can't see this, so I'm going to have to tell you what it says if I can see it. It's got a line for about 169 megahertz, for example. So right off the bat, we know that we have a matching network for something in the close to the 2 meter band. And then we have a line for 433 and a line for 470, and then a line up in about the 915 range, 910 range. And those might sound familiar because there are a lot of some of the commercial bands that are used in a variety of devices. But what I was really interested in knowing is, does this work in the ham bands? Because again, 169 megahertz, maybe not exactly a ham band, right? 433, 470, does that stretch across the ham band? So at that point, we get to continue our learning experiences here. Because I was extremely interested in doing some sort of simulation on the response of these, right? I didn't have test equipment and I didn't have the boards built. So what would happen if I plugged these values into that network into a circuit simulator? And here we go again, something new. This time I end up using the Quite Universal Circuit Simulator. Who has heard of the Quite Universal Circuit Simulator? A few hands out there. Who has used the Quite Universal Circuit Simulator? From now on, I'm going to pronounce it QUCS because I'm pretty sure that's how you pronounce it, is QUCS. But I ended up learning QUCS real quickly and realizing that I could run a S-parameter simulation on that across these networks. And so I ended up plugging their networks in for both the UHF and the VHF frequencies. And I don't have all the charts here. They're actually posted to my website. But what I did find is that these networks match quite nicely across all of the ham bands from 2 meters to 440. Both of those are very nicely matched with these networks. So that means all I would have to do to make this a 2 meter board is replace some of the components that I put on the board with different value components. So rather than putting the components on there that were out of that table for 433 megahertz, I could put the components in there that were for 169 megahertz, but it works really well at the ham 2 meter band. So it turns out that this board became a lot more powerful and flexible than I thought. I could match it to pretty much whatever band I wanted within the range of sample values. Now, if you chose an arbitrary band like 30 megahertz, something down the lower end, and asked me for what would the matching components look like for that, I would be deer in the headlights, having no idea where to start. I'd have to learn something new at that point. But, you know, you can imagine that there's a way to do that. So the board turned out to be successful. I've actually ended up building several for my own use, but I've also recouped my costs and provided them to some experimenters, so some AMSAT engineers, some AMSAT members, some individuals at universities that are interested in this. So it's kind of getting a few legs, and it's pretty exciting at the same time. So what's next? Well, I do intend to add an external power amplifier to it. So the 40 milliwatts isn't bad, but if you're going to do anything real, you got to reach a little bit further than that. So the AMSAT Golf project, the satellite project, is using an NXP component that picks up about 31, 32 dB of gain at 900 megahertz. It's a little bit more lower with reasonable frequency response for the UHF band. So I actually am planning to add a power amplifier to it. I'm also planning to actually put a GPS, or at least pads for GPS on it, because we have a lot of need to, you know, locate like satellite or balloon transponders, APRS uses, that sort of thing. So if we put a GPS on it, we might be able to basically have an in-box beacon, and that sounds like a lot of fun. Planning on putting a transverter on it for much higher frequencies. You're going to hear some presentations, I think, from Open Research Institute. Some of those may or may not talk about like the 5 gigahertz, 10 gigahertz bands that they're looking at, but that's certainly something I'm interested in, so I'm intending to look at the opportunity to put some solid-state transverters for 5 gigahertz at least onto these boards so that we can handle much higher frequencies, much higher data rates. And I'm also looking at the opportunities to build these for other processors, so Arduinos or some of these other single-board computers that Scotty showed us earlier. So there's a lot of cool opportunities, a lot of things we can do as an experimental platform to bring this to everybody. More questions, please. There was one question that I probably never answered. Let's get a mic to you. Let's get a mic to you real quick, and then the matching. I did answer it? That's because
So you anticipated the question.
I can see into the future. At least that's my claim. Other questions, please.
Okay, move along, I guess.
All righty. That's it. See, now I'm saying questions and answers. So please, more questions.
Any real questions now?
Yeah, this is final, for your final questions.
Is this your final answer?
Anybody? Anybody? Going once? There we go.
Okay, Will's got one behind you.
Okay, thank you. Actually, there's nothing directly to do with your circuit, but I'm actually about to get one of those reflow ovens, something like it. Did that, I'll put off topic, did that work pretty good for you? 'Cause
So
I'm
the
fine with
question you have for me is, I went out on a limb and paid like, $190 or whatever it was for a reflow oven. Does it really work from Amazon? And the answer is it's fantastic. I love that device. I have read some thare about how it may not be entirely temperature stable. But I've not had that problem. I've actually had to be very stable on the temperature. It's got built-in, what are they called when it raises the temperatures and soaks and, profile. Has built-in profiles that work really well. Push one button at the end of 10 minutes, turn it off because it doesn't turn itself off. And you've got a perfectly flowed board every single time. So that's a fantastic device. This particular one I didn't find on Amazon the last time I looked, but there are others a lot like it. So by all means, I can endorse it as much as my endorsement means something.
You heard it here first.
That's right. And they did not pay me a dime for that. Any questions? More questions? Well, thank you very much. I appreciate it. You have a great afternoon.